We are live now. Recording is starting now. Yeah, good to go. Thank you.
Okay, so Amritsar, shall I start now?
Yes, you can start.
Okay. Hello everyone, I, Kriti Vishesh Jaiswal from Navrashta University, welcome you all to the sixth webinar organized by the School of Engineering and Technology, Navrashta University, jointly with Thomas J. Watson, College of Engineering and Applied Science, Binghamton University, State University of New York, USA. Today's webinar is about additive manufacturing as a revolutionizing manufacturing technology. It has been adopted for numerous applications in biomedicals, aerospace, and automobile industries. This talk will discuss medical applications of 3D printing in combating the global COVID-19 crisis and in printing teeth modules for orthodontists. Now, I would like to invite Dr. Nilay Yajnik, Provost, Navrashta University, to shed some more light on today's event. Over to you, sir.
Thank you, Kriti. Dear Professor Michael Testani, Dr. Jia Deng, and all faculty, staff, students from all over India and the world who are attending this session, thank you so much for joining us today. This is a series of seminars which we are doing as a part of our collaboration with the Thomas J. Watson School of Engineering at the State University of New York, Binghamton. And there are several very interesting seminars that we've had all these weeks. And today's webinar focuses on additive manufacturing for medical applications. This fits in perfectly with both our schools' projects. And in fact, we have very recently set up an automation lab which combines 3D printing, CAD/CAM, a robot, CNC machines, everything together. So this will add tremendous value to our students as well. And I thank you, Dr. Jia Deng and Professor Michael Testani. I'm also extremely grateful to Dean Srihari, of the Dean of the School of Thomas J. Watson School of Engineering of the State University of New York, Binghamton University. Thank you so much for all your support all along. Welcome to all. Thank you.
Thank you, sir, for your inspiring thoughts on the program. Now, I would like to invite Mr. Michael V. Testani, Director of Industrial Outreach from Binghamton University, to introduce our guest speaker today.
Well, thank you, Professor Kriti. It's my pleasure and a privilege to be here. Thank you, Provost Nilay. It's always a joy to be here with you all. Consider you all as colleagues. Thank you to all our guests. Thank you to our speaker, Dr. Deng. I think you're in store for a wonderful talk today. You'll be impressed with the work that's going on in this space. And as we were talking about before the webinar started, you know, this is an area that I think really applies to a lot of different domains. Dr. Deng is from system science, industrial engineering, but this applies to mechanical engineers, biomedical engineers, and, you know, a whole host of technical disciplines, I think, have a strong interest in this domain. And companies are moving in this direction in terms of doing more and more with additive manufacturing. So I think this is an exciting space to learn about and an exciting space to be in. So I would encourage everyone to learn more and do more in the world of additive manufacturing. And I won't take up too much of your time. I just want to give you a bit of an overview of the Thomas J. Watson School, so you're aware of where we're coming from. And I certainly want to acknowledge all the organizers, certainly Provost Yajnik, Professor Kriti, Dr. Amarish, Waibab, Dinesh, all do a great job in terms of organizing these events. We all would not be here if it were not for all their great work and efforts. I'm truly appreciative of that. So again, welcome. Thank you for joining this series. This is number 6 of 7. So one more to go, and they've been going great. We're reaching hundreds, if not thousands, of folks around the world. So we're very proud to be here and delighted to have you all here. The goal of the Watson College as part of the Binghamton University is to provide world-class higher education in engineering and applied science. And we have a very, very strong international perspective, which is why we're here today, collaborating with Navrachna, and we're delighted to be doing that. Our students, our faculty are very diverse. We're very proud of our diversity. They come from over 50 countries and regions around the world. So, we like the notion that our university reflects the world, and our people and our profiles reflect the entire world. Just quickly, in terms of our ranking, there's a few here that I thought you might be interested in. We're very proud of our rankings. We're ranked quite high amongst other colleges and universities around the world. Kiplinger has us number 7. This is a financial magazine. Number 7 in terms of U.S. public college for out-of-state and international students. So we're certainly proud of that. We do have a strong international focus as stated. Money Magazine, best public university for return on investment after graduation. We are a great value. We work really hard to help supplement the students' educational experience by way of internships and on-campus jobs and other types of assistantships. So it is a very affordable education, and our students do extremely well following education. I think part of that is, from a graduate student standpoint, we stand on the shoulders of the great institutions in India, like NUV. You do a great job in terms of, your undergraduate and graduate program, but we're delighted to get your undergraduate students and then build on the foundation that you've created for us. And as I say, our students do extremely well. I talk to our alumni all the time. And they're senior director after 10 or 15 years in industry. They're directors, senior directors, vice presidents, CEOs of really some amazing companies. And, we all like to be number 1. So not only are we the number 1 public college in New York, we're number 1 in all of the Northeast. So again, we're very proud of our rankings, and we work hard to continue to grow, really the value that we're able to offer our students. That's our perspective. We have a number of programs in Watson College. Our speaker today is from System Science and Industrial Engineering, but we have Biomedical Engineering, Computer Science, Electrical and Computer Engineering, Material Science and Engineering, Mechanical Engineering, Data Analytics. So just about everything you'd want to do in the technical space, we are offering. And we're one of 6 colleges on campus as well. So if you're not interested in engineering, there's other schools for you as well. We're proud of the connections we have in industry. We've been around for over 70 years. So over that time, we've been able to forge some very strong alliances with some very, very important industry partners. So this means internships, this means pathways post-graduation for our students. And those things are important. I mentioned how well our students do post-graduation. Here's Hiran, right, who's now the Director of Project Management at Qualcomm. So doing quite well in his career. And you can see what he has to say about, Watson College, had amazing professors, and he was, an excellent student as well. And as I say, he's doing really well in his career. And this is not unusual, right? This is not an isolated story. I talked to dozens of our alumni who have the same story, who just met amazing success. And that's our goal, is to prepare our students for success. We're also proud of a fairly recent accomplishment at our university, where Dr. Stan Whittingham was recognized with the Nobel Prize in Chemistry for his contribution in the invention of the lithium-ion battery. So the computer, the tablet that you're watching this webinar from, or the cell phone that you're using after the webinar, is all powered by Dr. Whittingham's invention. So we're just so proud to have him as a part of our campus and a part of our programs. And as we're saying, we have this collaboration between NUV and BU. It's a joint webinar series. It's the success of this program is really due to our leadership, Provost Yajnik, our Dean Srihari here at the Watson College, Dr. Amarish, and I'm proud to be collaborating with all of you. This is number 6 of 7, as I said, so you can see what we've covered in the past. And, we've got one more seminar left to go here on July 16th. So we hope to see you back for that webinar as well. But without further ado, you're here to hear Dr. Deng and, learn some things about additive manufacturing. So it's my honor and privilege to introduce him. Dr. Deng has been a part of our system science and industrial engineering program for the past 4 years or so, joined us in 2017. You can see he received his PhD from North Carolina State University, which is an esteemed university. His research interests are process innovations and applications of AFM-based nanomanufacturing and additive manufacturing in biomedical fields. So, it's my honor and privilege to be introducing Dr. Deng. Gia, thank you so much for being here with us today. And we're really looking forward to your webinar. So with that, I will turn the floor over to you.
Sure. Thank you, Mike. It's a great introduction of our university and our awesome college. And also thank you very much, Ms. Gritty and our provost, Nile. Thank you very much. So I'll start share my screen and we'll get started. So here is the presentation. Please let me zoom in. Mike, could you all see that? All right.
Yes, it's in presentation mode. It looks great.
Yes.
Thank you.
Thank you for the information. So thank you, everyone. Today, my topic is going to be additive manufacturing for medical applications. So today's the contents, I will cover three kind of topics. First is the introduction. So maybe some of you already know at least some of the additive manufacturing. I would like to briefly introduce that, some details. And also I would like to talk about additive manufacturing on combating COVID-19 in the past year or so. We've done quite something, especially in early 2020. And specifically, I'm going to talk about ventilator adapters, face masks. And also beyond that, I would like to talk about additive manufacturing for orthodontics applications. Okay, so first a little bit introduction of our additive manufacturing facilities at our Watson College. As you can see here, we have a bunch of existing devices that we can use on campus. So first of all, we have metal printers. We have quite a lot of variants of those metal printers. For example, we have an EOS M290. As you can see, the EOS M290 is like a very big device. And as you can see here, this one is the EOS M290. So it's very kind of high quality and expensive machine. And you can see there are some of the powders can be put in and laser going down, can do 3D printing. And we also have some other
I guess we lost the connection.
I think, yeah, I think Dr. Deng is frozen. So let's see if we can reconnect.
We cannot hear the voice by Dr. Jia Deng.
Yeah, it seems his screen is frozen. I don't know if this will help. I'll stop sharing my video and it might free up some bandwidth. Dr. Deng may want to do the same when he reconnects.
Dr. Deng? Dr. Deng, your audio is not reaching us.
In fact, screen sharing has also stopped, so there might be some issues.
Yeah, that's right.
Yeah, let's see if he can get reconnected and rejoin us here shortly. Apologies for the technical glitch. Let's get it resolved and we'll get back on track here. Thank you for your patience.
But is Dr. Deng aware that he's unable? I mean,
He's He
I
is
think,
joining
sir,
again.
he is not in the meeting. I think he
He's
lost
joining
He's left the
again.
meeting.
connections. Yeah, he's not in the meeting right now.
Yeah, so we'll get him back in and get reconnected. Let me just check my text and emails, make sure his internet didn't drop.
Yeah, he's joining again.
Great. Okay. Thank you for your patience, everyone.
Dr. Deng, you can unmute your microphone. Dr. Deng? Yeah. Dr. Deng?
Yeah.
Yeah.
I think he is sharing his screen.
Yeah.
Okay, the screen is back. Dr. Deng, we can see your screen. Don't have your audio yet. And if
it's
it's a bandwidth challenge, gee, I don't know how much it would help, but maybe closing the video camera, the webcam might free up some bandwidth. It's up to you if you want to try that.
okay. Okay. Can you hear me? I can
Yes.
hear everything.
Yes.
Yes, now we can hear you, sir.
Okay. Okay. Thank you. So now my voice is okay now? Or?
Yeah.
Yes, sir. Yes,
Yes,
sir. You are
very
audible.
clear. Yes, and you cut out when you were talking about the equipment. Yeah,
Okay.
yeah,
over
slide
here.
3. Yes.
Okay. Yeah. I think it's some of the bandwidth issue. So I'll just continue here, and please let me know if still any voice issue, any other issues. Back then, I thought I can hear you, but it seems like my voice is not reaching to you. But I'll just continue here. All right.
Great.
So
Thank you.
Thank you very much. So I'll continue introduce our AM facilities at Watson. And we do have metal printers. As you can see, this is the powder bed fusion powder. So you can see this machine can be used to print metal powders, and then using the lasers to do 3D printing using the metal materials. And also we have a Metal X system. We are able to print the material of the all kinds of metals and make it on this device. And we do have some research equipment as well that can be used for metal 3D printer. And beyond the metal material printers, we can also print some of the polymer materials using all kinds of the machines, such as this big loose bot and the Mark II and some Form 3, Form 2 polymer printers. And beyond that, we know inspecting the quality and the shape is very important. And we do have 3D scanners as well. In our Watson College, we have a lot of hands-on scanners. We have micro 3D scanners, has higher resolution to do scanning. So those are equipments at our Watson College. And also testing facilities, we have something can be used to do more tests, such as optical microscope, universal tester, optical micro profilometer. It can be used to scan three-dimensional 3D printer results, and we can do some post-processing using the CNC machine, board jetting machine. And also beyond that, we can have other equipments to do TEM, SEM, micro CT, XRD tests. So all those are facilities we can use for 3D printing experiments. So for introduction of the 3D printing, so 3D printing has a lot of applications in all kinds of area. And first of all, I would like to talk about 3D printing in automobile as one of the three pioneers that has been used and adopted 3D printing very long time ago. And so nowadays, many automobile companies already started to adopt 3D printing. So for example, those car companies, especially example is Ford, they printed and tested over 10 designs for front splitter wickers, which they were able to simultaneously send out for test evaluation. So this one is a Shelby GT500, is a very fancy car from Ford. And you can see the front has a kind of splitter here. And 3D printing can be facilitate and make it faster to design and test out the aerodynamic design of this new advanced Mustang machine. So continue with that. Not only Ford has mentioned, a lot of automobile company is trying to engage with 3D printing. And Porsche find a good way of that is a lot of advanced cars and fancy cars. They are quite old, but they don't have any backups or plans to mass producing those old kind of out of dated devices or shapes or some part of the components of the car. So they use 3D printing to produce some rare low volume spare parts for its old inventory. So for example, some of the cars actually just missing one part or a few parts. So there's no reason for the Porsche to actually get a mass production line or something. So they can use 3D printing to actually produce individual parts for whatever needs. And for that is 3D printing for the automobile. We have some applications and also some existing work ongoing in aerospace. So GE Aviation is a trailblazer for metal additive manufacturing products. So the fuel nozzle for the LEAP engine. So firstly, a few years ago, is firstly in April 2016 to equip it onto the Airbus. So as you can see, there are already more than 12,000 orders for the LEAP engine, and also already 3D printed a lot of nozzles by October 2018. So by 2020, already more than 120,000 parts by the AM for this the LEAP engine. So as you can see here, this is this is a nozzle 3D printed out and equipped for the LEAP engine, because the LEAP engine is quite inside the airplane. So maybe along some traveling, when you're traveling using the airplane, you didn't notice. Okay, it has already been equipped, right, in the flying airplane, but it is already there. And also we have we can see this another picture. So GE Aviation also have some production and also other locations to do producing those machines for 3D printing, or to do the production for all kinds of applications in aerospace. So these are some results and examples for 3D printing in aerospace. And also 3D printing in biomedical is definitely
Did we lose our others hearing Dr. Deng? I'm not getting the
Hello?
audio.
We cannot getting your audio, sir.
We're not able to hear you, Dr. Deng.
He is still in meeting, sir.
Yes, sir. He is in
But
the
we
meeting.
are unable to. Hello, sir. Can you hear me, Dr. Dang? I think
Dr.
so.
Deng, you
Again,
can.
we lost connection.
If he's in meeting, can we unmute him by mistake? Not
He is
muted.
already unmute, sir.
Okay.
Just video is off.
So I think there are some bandwidth issues from his side.
I'm
Yes,
here.
sir. I am here. Jia
He is
Deng, sir.
here.
Yes, sir.
Okay,
Deng, sir.
we're just not able to hear you, Dr. Deng. May have lost the connections. Maybe reconnecting again.
I think if all of us are turn off our videos, then it may help him probably.
May open up some bandwidth. It's good. It's worth
Ah.
trying.
Okay.
Hello,
Hello?
Dr. Deng. Could you try speaking?
Hello? Yeah, hello.
Okay,
Hello?
can hear you now. Yes.
Yes.
Okay.
Great.
Yes,
Okay,
audible.
okay,
Continue,
okay.
sir.
Okay. Yeah, really sorry for any those interruptions. So probably I still I'll probably still have some other maybe issues or anything. What happened to network? I'm really sorry.
Sir, we are unable to
No,
Can you
see
hear
sir.
me
your
now?
screen right now.
Yeah,
Yes.
yes, it's visible. Please continue, sir.
Okay. So can you hear me now?
Yeah.
It's good.
Yes.
Okay, I'm really sorry about the inner issue. So let's keep going just in case anything happens. Please let me know. But I can hear you all saying that you cannot hear me, but I don't know why my voice is not going out. So I'll just let's just keep going. So 3D printing in the biomedical. So the Lima corporate from Italy. So you can see this is the example that's showing up the titanium alloy for the devices more than 10 years. And we have a lot of needs actually for replace this structure over here connecting to the to the backside of the hip. And as you can see, each and every one has its individual different shape and it is not easy to meet all the needs if we use mass production, right? So that's why this company produced the 3D printing results, trying to meet up every customers and then to make things much easier to produce and understand. So 3D printing in the dental and the dental applications is some of the application areas. And as you can see, this is an example. Use 3D systems to produce the dental application. You can see it's all 3D printed the metal parts. And also there are some other examples can be printed by Stratasys, and you can see the liners and some other shape models. And as another thing that's possible is in dental area, we have 3D printed coping, metal casting, and some other layers. And you can see all kinds of shapes, materials, and the way different applications. Those that can be 3D printed in the dental. So 3D printing as an overview status in 2017, as you can see here, 3D printing applications has a prototype about 34%, and proof of the concept is about 23%, and production, etc. So you can see those two are pretty kind of the pioneer or mostly utilized in 2017 about prototyping and proof of concepts. So moving towards the 2020, 3D printing status got increased a lot. Again, the prototyping is a kind of highest percentage, and also following up by the proof of concept and the test models. So that goes to the application process chain. So to a little bit go in a little bit details about how we actually utilize 3D printing from the very beginning of the CAD model all the way down to the application. So first is the CAD model. CAD model we need to design using any three-dimensional software to design whatever results that we need, shape we need to print it out. And also secondly is we need to transfer from the design towards the STL file, which is a language that can connect your design with the machine. So after getting the STL file, then we need to do some of the cutting and some of the kind of communication between STL file and the machine, that is slicing. So by detail setting up the layer height, layer thickness, and spring speed, temperature, those details, the machine can be controlled to do whatever printing as you need. And following up is some other process such as machine setup, build, remove, you can see, and also finally is the post-processing and the application. So try to dig a little bit into the STL file so you get a more sense of. So this is a language that can communicate between your design and the machine, the 3D printer. So what is STL file? So STL file is actually based on the full name of stereolithography. This is invented by 3D System in 1990s. So as you can see, STL file can be also called standard triangle language or standard tessellation language. Never mind, it is just a language. So actually what it looks like is if you want to show up the kind of two circular shape, which is partial of the torus, and you can see we can use a lot of triangles. So those triangles can connect those together, occupy the inside inside space and geometry to make sure it is kind of more or less mimic the actual curvatures. So as you can see here, we have the examples of different STL file resolution. We can have low resolution where we can have only use 4 triangles to represent a curvature, but we can also increase the number of triangles to make it easier to be more smoother, and so the machine can have better results. So from a few triangles from 4 all the way to 96 triangles, as you can see, it is much more smoother, right? And so that is the STL file changes. And also you can see here you got design, and you can select the different number of triangles, and then you can see this is the STL file that representing the same design. So that is the design. So as you know, sometimes you're not only do the designing and do some production. Sometimes you will need to do some reverse engineering or using existing model size to do some of 3D printing modeling. So we need some of other 3D modeling technologies actually to do some of the modeling process instead of only do the designing, right? So the CMM is quite a familiar machine for the conventional manufacturing process, but this one is can be also used for 3D modeling to scan three-dimensional objects. And also similarly, we have laser scanning, specifically nowadays very popular, and we do have equipments in our engineering Watson College, and students can use and hands on that. And also we have the structured light scanning and some CT and MRI and photogrammetry. So those are all kinds of 3D modeling techniques that allows you to recap some of the existing shape or color or kind of geometry. So able to do that. So I'll use one thing very interesting as example is photogrammetry. So photogrammetry is utilize a lot of photos and to make stitching them together as a 3D modeling technique. As you can see, I've already used up some of the papers or say pictures being stitched together into a three-dimensional model. So this is a small puddle in my office. So you can see this is the final results. And outside those dots shows location of the camera. And it shows how you take the pictures using your cell phone, actually round it along this three-dimensional models that you would like to do the 3D modeling and maybe then the printing. So as we know, we have designing, we also have the scanning to do the model construction. Most of the time for 3D scanning or some other modeling or for reverse engineering, so we need some of the repairing procedures. For the STL file, you can have the repairing software to actually fixing those errors that in the three-dimensional models. As you can see here, this is original three-dimensional scanned results. You can see there's not perfect. There's some defects here, over there. And all those are actually not give the users the difficult time to do 3D printing. And we can use some of the software to do fixing and then repair all those defects. And I do talk about those process in the class. So after finishing up the either fixing or any other process, we have the STL file already finished, ready to print. So we need to be careful about the printing with some support structures, because some complex geometries, as you can see here, is actually very not easy to hold, and we need some support structures to support those materials to make sure we don't print anything from the air, right? So it might generate some defects or anything. And another example is this cap, and you can see all the bottom parts will need the supports to make sure the copy is perfectly printed out. And similarly, there are some definitely, if any bridge structure, you can see a kind of 90-degree angle, and anything protruding out from here, we need some supports. Otherwise, we'll have issues about trying to hand all those structures. Otherwise, those noodles will actually get showing up the defects of the results. So those are means supports. We need to be careful. And following up, I'm going to talk about machine setup, the build, and the remove process in this AM process chain. So for it depends on different materials, different machines. We use different specific things. So fused deposition modeling is one of the 7 standards in the 3D printing in the additive manufacturing. So as you can see, the fused deposition modeling use those filaments to print out the three-dimensional shape or results. And those very important, very popular FDM machines includes this Strata system, and that is from a company. This is a company name, and this model is Uprint. And also we do have many other companies with different kind of shape type of the machines, and they can process a lot of materials such as ABS, PLA, nylon, and PVA, PC, etc. So fused deposition modeling is a very popular process for the material processing and 3D printing. And actually, I'm just talking about the material extrusion, and we actually got 7 categories, standardized categories in the 3D printing. So those will have different results and the possibilities. So that is the first introduction of our additive manufacturing. So it actually shows up that we do have a lot of things we can do. And next, I will talk about additive manufacturing for combat COVID-19. So I'm going to talk about the two examples. So 3D printing actually very popular for all kinds of shapes and customized results. And another advantage is it can actually locally print and support our local healthcare workers. And back in 2020, March, April time, so it was very in short of a lot of masks and some other PPEs even in our local healthcare industry. So those hospitals actually will need some of the things. And here's this picture shows a student of mine is working on printing those face masks and the ventilator adapters, and we got a news that being reported not only in our university but also in the local news, and has been spread to the entire United States. And our two parts, one is ventilator adapter, another is face masks. I'll gradually talk about those one by one. So first is the ventilator. So actually the ventilator, I think we actually all understand what is ventilator now. It is being used to help with patients that cannot actually actively breathe. So that will need some ventilator. But usually one ventilator is being used for one patient. But now because of those all kinds of supplies are in short, we would like to find some way to actually make the one ventilator be used for two patients. So you can see maybe those patient lungs can be ventilated. So that means there will be needs for all kinds of like one way extended to two ways, and then coming into a lung and then go back to this machine. And then this one shows, okay, it's very much a lot of connections areas that the ventilator adapters with using those adapters to be able to accommodate more than one single patient. So because of the needs, so we firstly designed some 2-to-1 ventilator and 4 outlets. So as you can see that we actually at the very beginning designed some of these, a few of these, so that one inlet can be split into two inputs and outputs. So as you can see, one can be double into two. So then we actually design print some of these and be able to connect together, so that even when we are able to print these, so it can either be used for 142, or when we actually combine them together, it can be used for 144, because inlet is here, then we got 4 outlets, 1, 2, 3, 4. So that was some assembly parts, and we do have something and produce something. So however, then we realized that actually we can, sometimes it takes too much time to print those 142 or 144, and it's easier to fix it into either 122 or 124. So as long as there are needs, we can just make it optimize, make it better design, and then get some things that we can actually utilize those techniques, other than just has to manually assign those parts. So we actually changed the design and make it 144, looking like this. And so you can see it one input, you can get 4 output. So those 4 output can be used for the input for the lungs. And we got some preliminary designs, and we also keep going, keep optimizing the design. And finally, we got shorter ones, smaller ones, make it as small as possible as we can. And we talk about the supports, because if it is a circle, it is highly likely we'll need some supports. So we actually design an inner triangular shape, so we don't need any of the supports inside, which is very, very hard, very difficult to remove. And then we'll get some updated design and print them out, send out to our local hospitals for the test. And also we kind of design some other things, 144, just in case any needs. So those are our designs results, some results, and also even the 1 different design 126. So we finally got a lot of results, and then as you can see, we mentioned about that it's a kind of adapter for the ventilator. But in order to make sure everybody is safe, there's no cross-contamination, we need to use the filter. So the filter has to be fitted very well, tightly with the inlet. And also for the output, we also need some of the filters over here for 4 of them. So that means it's going to much better prevent any cross contamination. So those are equipped with, you can see the HEPA inside filter, and outsides are we make sure the 3D printed parts fitting well with the filter. So that was the design for the adapter. And we also design and trying to help out with some face masks. A colleague of mine utilized the TPU and the PLA double materials to make a kind of flexible mask. So the entire mask is quite flexible, because you can see the green color here is actually the TPU, is a material that is flexible, and it was quite a good strength. So the design is like this. We got TPU materials, and we've got PLA materials, which is a little bit rigid, because people are trying to put some of the filters inside, so we cannot destroy the filter easily. And then that's why we use the PLA to do the this kind of materials. And also this is the overall design, shows the design and the results. So to enhance, basically, as we know, this is 2 materials, but double materials will have the issue of actually connecting together, especially when one is quite flexible. Another PLA here is actually quite rigid. So a student actually designed some of the interlocking design, so that those two materials actually can be combined together and printed out together using 2 nozzle fused deposition modeling machine. So by optimizing the printing parameters, so fully dense TPU surface can be obtained. So this one, you can see this is a result. It shows it's pretty smooth. Under 40x optical microscope, we can see much more better details about this TPU results here. And I do have one small video that might show the, let me see. Okay. Okay, so this is this example that's showing up that while it's printing, there are some PLA materials already printed out as the previous layer, and then the printing head is switching to another printing head, and be able to cover the previous the PLA materials. So those TPU green materials can cover on top and make things locking well. Okay. So next, so my group also kind of optimize and design another face masks. Actually, is kind of rigid inside, but there's a sealing, very flexible covering materials at the outside. So this one, the inside is PETG materials, and the sealing is the PDMS, and the inside of PETG is very rigid materials, and outside is flexible. So this face mask are designed and equipped with this very unique and that can fit on different kind of shape or size of the faces, and make it attaching on the skin very well. So the virus cannot actually go from this kind of very strange shape, right, connecting area, so to fully protect the health worker. And also we can use any sort of HEPA filters with 95%, 99% percentage of the filtering capability. But one thing to keep in mind is if we use HEPA filter, which is 99%, it will have a little bit difficult time for the healthcare workers to wear this face mask for a long time. And the way we're doing this is we do 3D printing of this part, and that is rigid. And we're also trying to create that sealing top on the rigid mask. So what we do is we actually design and also 3D printing this mold to actually create the very complex geometry of that sealing PDMS on the top, right? As you can see here, the entire this is this is two parts of the mold. One, we can pull in the materials inside. It's gonna have kind of fitting all those areas, and also our designs, and we'll be able to see from another hole to actually get out of the air. So this is the inside geometry, that what it looks like to actually inside the mold. As you can see, we got some 3 pins. So these 3 pins can actually make sure them molded, fitted well together. And also the shape, the geometry is the reverse of that surface of that face mask. So make sure the molded parts can be actually on the top of that rigid mask. So we actually use a stereolithography printer, which is the printer I mentioned that in our Watson College. We utilize that. Okay. Okay. So I'll just keep going. Right? So so we do have the machine can do the very high resolution printing to do to use for our mold production. So continuing, so this is the result showing that we have the rubber structure looking like this. This is the results that we're showing up. Some of the typical results directly came out from this 3D printed mold. And as you can see, we have those kind of the channels that are used for filling the materials. And we also have some of the defects maybe that can be generated a little bit. We need to tune up those locations just simply by scissors, and we can get very good results to fit up on the PETG material, that hard mask. So those are the results, shows our different designs, updated results. As you can see, we have some of the the version of the mode, and also we have some other updated mode to decrease the printing time, and in the bigger ones, a little bit smaller size, to accommodate different face shapes, right? So because we have those different modes, we are able to use the flexible materials, and of course those are biocompatible, so it's very safe for people to touch on people's skin. And a lot of coverage on this, and from a little bit larger size, smaller size, you can see we can accommodate different usage. So those are some of the results. And of course, some of my other colleagues in Watson School, so they work very hard to do this face shield. So this face shield actually produced by first 3D printing some geometry looking like this. So all 3D printed, and then kind of bended them together and to fit different size of the head. And for this one, only need to use very thin materials to cover on those pin areas to make sure it is the very useful face shield. By that time, we're actually in short to provide those face shielding devices. So those are the second section, and the last example I would like to talk about is additive manufacturing for orthodontics. So it's about the teeth modeling, printing, and quality inspection. So for a lot of people probably at least notice or have done some of these kind of using some braces or something. So traditionally, when the teenagers got trying to fix up those the teeth shape, and typically they use the braces, right? You can see a lot of braces put on the top, and then the patient has to open their mouth for a long time, and sometimes the patient, the orthodontics office, they will need to adjust those location, shape, the force. So it takes a long time, and actually the patient is not very feeling well. And sometimes because of the just the experience based, got a little bit force in this area or a bit force in that area. So there are some conventional ways, but because of 3D printing, so now in the many orthodontics, they actually try to upgrade and make it more modern and easier for the patients to actually to just come in and go, and reduce a lot of visiting time, and also it will increase the maybe increase the results and reduce some of the pain that caused by the experimental based force apply. Okay, so what they do is actually, as you can see, what they do is they have the scanner, 3D scanner. So this 3D scanner can be used to scan all the shape of the teeth from the different patients. You can see people actually have very different shape and size of the teeth. Okay, so the issue is, in order to decrease the visiting time, so the orthodontic office will need to 3D print it out, that scan data, right? Scan data can be 3D printed out. And also the dentist already have, or orthodontist already have the 3D printed parts. And then they can spend the time, they can visualize that because when they handle this, they don't need patients to open their mouth, and much more easier to handle and take a look at where is those areas, how to put the proper location for the different tiny device here, right? So 3D printing, that's how 3D printing plays a role, just of the using those braces. As you can see how this plays a role. So, but by looking at that, I always had a doubt asking them that, say, okay, have you ever, how do you guys make sure that confident that 3D printed parts is exactly the size of the patients, right? How about maybe any printing issue, manufacturing error or something? Is it possible? Ask them. They say, okay, 3D printing is good. I trust it. They didn't actually get some research on it, understand the process, the quality. So this is my my research is about. My research group did something about like this. First of all, we got a raw file from patients looking like this. So right after scanning, we got something like this. We need to clean the file from the patients and clean it up as a 3D printable, and then we actually 3D print it out. Then we got the 3D printed model, right? And the model can be rescanned. If it can be rescanned, so you got a new teeth model that is not from patients, but is from 3D printed results. So if you were able to compare the patient's results, either this one or this one, just cleaning some of the kind of defects somewhere, but overall size is the same thing. So we can compare the file from patient's teeth model or file from printed teeth model to compare. Okay, how much difference is any kind of large gap, right? But we use we actually use one same 3D scanner to do the thing, to make things quite consistent. So what we have done is actually we use compare those digital models of the by two different ways. One way is the analyze using the cloud compare. So they find those two different digital results together, and then be able to compare. Okay, so be able to compare those results, and also we're able to compare the Dragonfly software, and it can compare those in detailed results, such as interconnecting those very important location on the teeth to make sure they agree. And then we compare the results. So the registration results in the cloud compare is, as we can see, using one software, we can see some kind of the compared results, okay? And we can see there's, of course, we use some numbers because these are some from the patients. We need to kind of protect their kind of privacy and name, etc. So as you can see, after connecting those two components together, as you can see, they're already aligned together. And the color shows the difference of those two models. If you see red, that means one model is a little bit a larger distance, a little bit different, and another, the blue color shows, okay, another direction of the distance. But as we can see, there's a tiny distribution at the top to show the actually the same or difference, and the color is about a green. As you can see here, is pretty uniform. Just give a rough idea, showing up, okay, where is some defects, where are some of the results, very visualizable. And this is our results in Cloud Compare. And you can see our maximum distance region is not on the top of the teeth. It's actually on top of some of the support structures of the teeth, right? And then that's why we don't worry about at least from the Cloud Compare, it is pretty good, all right? It is aligned them together. And then we use, actually, we need to kind of measure those very important 8 measurements in another software. So 8 linear measurements for the upper and lower parts. As you can see, we have the canine midline, canine midline L right, and intercanine, interpremolar, interpremolar first, second, and intermolar. Those are all the 8 very important measurements. We need to do the measurements and compare the differences of those two models, 2 teeth models. One is from the patients, one is from 3D printed parts. So they will, because of that purpose, we're able to input that into the software, and then we're able to compare. As you can see here, we are able to measure and align and find those locations for the 8 measurements. And here, we got some of the upper patient measurements and upper rescan. As you can see, all the details, the pinpoint, that means the maximum height of that one, and different layers, locations be measured for different patients or the rescan. So as you can see, this is how we actually make sure our measurements select the correct location. We do have the measurement, we do have some of the points. If we slice those 3-dimensional data into different layers, and we find out those locations, make sure those points are the highest points on the teeth. That's why we make sure a distance is correct. So we measure 8 different results for each upper or lower, and then we got 4 patients, right? So as you can see, we got the all the results shown up here, and we measure all those 8 very important locations to make sure they aligned very well, and we compare. So basically, this one shows 247, got the one location which shows the maximum distance between the patients and between the 3D printed parts. So we do the pair t-test. As we can see here, it shows actually the p-value is quite okay. It's quite not significant. It shows that our results are very close. And we also try to calculate the percentage errors. And you can see the maximum here is about 5% in one specific location, but most of the time is about less than 1%. So you can see always point something less than 1%, and some of the twos, some of the ones. It depends on the length, locations. So those are the percentage errors for all those measurements. And we also plot them together, right? And you see all those kind of arrows, individual parameters for the 8 location measurements. This is patient 1 and patient 2, patient 3, patient 4. So you can see those are the actual results. About one is actually left percentage and rescan. And as you can see here, we also have the upper and the lower models. Most of the errors is about 1%, lower than that. Only one sample from a patient that is a little bit higher, about 2% for this specific patient. And also we can visualize the over percentage error in each patient. Different patients at different error rates, and most of the time still less than 1%. Only this patient got a little bit over than this 1.4 error. So that shows our 3D printing results is actually very comparable, very details, very good, connecting with the patient's teeth, right? So that means the orthodontic office can actually use that as the new device without any worrying, saying, okay, those are all the results. So the conclusion is no statistically significant differences between the dimensions of teeth from patients and 3D printed teeth models. So the maximum error is really kind of manageable, controllable, acceptable, right? And so those are our actual 3D printed parts, as you want to see. Those are by the stereolithography printers. Okay, so that's all for today's presentation. And I would like to really thank you for joining. And I would like to apologize for those network issue, if anything. So now I'm open to any questions. Please let me know if any questions. Thank you.
Thank you so much, Dr. Deng, for sharing your valuable opinions, findings, and knowledge with us today. So now session is open for questions and answers. So participants, if you have any questions, you guys can ask.
Hello, ma'am.
Hey.
Hello, Kriti,
Hello.
ma'am.
Yes, sir.
Yes,
Yes,
Pavan, sir.
there is one question from the participant. What is the average time required for each of the orthodontic diagnostic procedure?
Okay.
Hello.
For those steps?
Yes, sir.
Yes.
Hello? So are you talking about those the procedures? What are time
Yes.
spending,
Yes.
right?
Yes, sir. What are the average time required?
Okay, thank you. So the process actually depends on the procedures, depends on the machine, and depends on what type of 3D printing techniques. For example, the fused deposition modeling, some of the machines we've seen. For example, those machines depends on different materials. It usually depends on also the size of the printing, from quickly less than 1 hour to as long as maybe more than 24 hours is possible. So it depends on the machine, depends on the materials, depends on your design, depends how big is that design, and what is the infill percentage. Many of the things can involve. Is that kind of answer the question?
Yes,
Yes,
sir.
sir. Thank you so much, sir, for your
Yeah,
answer. And I also received some questions from the participant side. And the question number one is, additive manufacturing method is most used to manufacture patients in specific implants.
Yeah, sorry, I hear some noise. Could you say that again?
Hello.
I couldn't.
Yes, sir, sure. Which additive manufacturing method is most used to manufacture patient-specific implants?
Yeah, so for the implants, many of these categories can be used. One and some other is for the plastic printing is all possible. Depends on the needs. For example, some of the one example is I show this company. A lot of the titanium alloy is for implants, and also there are some other examples such as for the scope for the scale the skull of human beings. So the skulls have some missing parts. The plastics can be also utilized. You just using maybe a few steps or some other things can also do that. It depends on your application location and your needs. So a lot of things can be used.
Okay, thank you
Thank you.
so much, sir, for your answer. I have another question for you. What are the
Yeah, go ahead.
softwares currently used for AM?
What are current what? The trend?
What are the softwares currently used for additive manufacturing?
Okay, the software. So the software, there are many softwares can be used from the designing. Let me share that. Find out the screen and let's talk about that. And from designing, as you can see, we need the design software, and also we need some STL file repairing, as I mentioned before, and also we need some of the support generation results, and also software, and also we need to use some of the different kinds of 3D scanning software, and including its hardware, of course, to actually get some results for us to do printing. So one thing is photogrammetry I introduced that doesn't need any hardware. So this cell phone can do the imaging, and some software can do the converting to digital results. So those are some things softwares will be involved. Actually, I teach a lot of the softwares during my class, so people students actually can hands on those and understand how to do those, and actually finally will generate some of their own results, their own 3D printing parts. Thank you.
Yes. Okay.
Nainil wants
Yes,
to
with
ask something.
Ma'am,
Hello.
Nainil Patel want to ask the question actually.
You can
Yeah, go ahead.
unmute Nainil. Yeah. Nainil, you
Yes.
unmute yourself and ask the question.
Yes, sir. First
Yeah,
of all,
please.
good morning to the presentees. My question is very specific towards the file conversion formats. So I'm an alumni from Navrachna in mechanical engineering. My question is, how can we convert, not convert, how can we reduce the size of SL, the file format which you showed STL? How can we reduce the file format for that for incorporating thin features?
Yeah. So the STL file, there are some softwares they can do the STL file repairments, changing, and fixing, and tune that the STL file. The software can do that. So you can make it if you wanna make the thin wall a little bit thinner, and you can just do some of the very kind of straightforward using those softwares. You can handle those STL file, so you can make it thinner, and then you can print it out. Is that answer your question?
Yes, sir. And also upon researching, I found that we can also use 3MF file. So is that compatible with our desktop FDM printers? Because in Navrachna we have one which is FDM printer. Would 3MF file be supported?
It probably will take some time. So far, most popular is the STL file still so far, but the different company, they have their own software or different, because for example, the Strata system, they have different colorful results. So they have their own kind of file size, file type is it is different. So for the STL file, most of the time is quite popular. Almost all 3D printers can accept STL file.
Okay. Thank you, sir.
Thank you.
yes, Mr. Grammy,
Yes.
you can ask your question.
Yes, Prashant sir, please go ahead.
Yeah, please.
Good evening, sir. This is Prashant from NIT Andhra Pradesh. I'm a
You're not audible, Mr.
research
Prashant.
scholar presently. Sir, is my voice
Actually,
audible?
sir, your voice is cracking.
Tracking.
We are unable to hear you properly.
Meanwhile, you can do one thing. You post your question. We will read and we'll ask the question on your behalf.
So you can send me your question to me.
It's okay, ma'am.
Yeah. Meanwhile, Mr. Jia,
Ma'am,
Dr. Jia,
ma'am,
Yeah.
there is a question I received from that sir, Prashant sir. Does the orthodontic implanted in child can grow with his age if implanted in child?
Sorry, I couldn't hear clearly. Could you say that again?
Sorry. Yes. Does the orthodontic implanted in child can grow with his age if implanted in child?
Yeah, there are some research. There's something, especially some startup companies is doing this. I believe yes, there are something is ongoing. and maybe not that popular or something, but it's definitely ongoing.
Okay, sir.
Yeah, thank you.
Sir, I received another question from the participant side. What parameters are important in selection of material in additive manufacturing?
Okay, thank you for the question. So how do you select the materials? It depends on first of the your needs. Do you need strong ones, or do you need polymer? Do you need metal? So first of all is your needs. Like for example, some implants are metals. Some implants are plastics. It depends on your actual application location. So that is one way to consider about the materials. And also is for, you need to think about the machine. If you have some machines that is readily available, and there might be some limitations on the machine. For example, even though those we have multiple different kind of the printers. For example, this one mostly is used for metals, even though it can use for something else. And for this one, for example, it can mostly use for kind of thermoplastic polymers. And this is for the photo curable resin. So those are different materials that you want to use. So also one consideration about that. Thank you.
Thank you so much, sir, for your answer. I think I can take one more question. And the next question is there a limitation to what shapes you can 3D print?
So far, in terms of shape, I don't think there are any shape limitations.
I think so, sir.
Yeah, thank you. Yeah, I don't think there are any shape limitations. So even though there are some considerations, there, for example, some of the support structure, you need to think about how to get it off afterwards, or the how small you want to do, and how big you want to do. Is the machine big enough? But in terms of the shape only, I would say it is very possible, almost everything.
Okay, thank you so much, sir, for your answer. Actually, I received several questions from the participant side, but due to the time limit, I am unable to ask you each and every question. But I will do one thing. I will send you the email to Professor Mike, and he will forward those questions to you.
Yes, no
Is it
problem at
fine,
all.
sir?
Yeah, please feel free.
That would be great.
Okay, so thank you, sir, for your answers. Thank you, everyone. As Marcus Specher said, the students of the future will demand the learning support that is appropriate for their situation or context. Nothing more, nothing less. Now, I would like to invite Dr. Amrish Bhattgujjar, Head, School of Engineering and Technology, Navrashna University, for the concluding remarks.
So, first of all, thank you, Professor G.R. Deng, for giving a wonderful talk on the additive manufacturing and its application in medical field. It is you started with very basic things, and you take on to the kind of research that is you are doing in Thomas J. Watson College of Engineering. And you also elaborated means during the pandemic how your laboratory and your group has helped the developing the face shield, face mask, and other devices for the medical application. So I think all the participants might be delighted with the kind of work that is you are doing at your laboratory. Thank you once again. And at this moment, I also would like to thank your Dean, Dr. Srihari, as well as Provost Dr. Nilay Yagnik for supporting this events, supporting this series, NUV-BU seminar series. I'm also thankful to Professor Mike for constant support, Professor Kriti and Professor Vaibhav for just spreading awareness about this seminar. And because of all the cumulative effort, this particular series is doing very well, and it is gaining success day by day. And with this, I once again thank all the participants for their precious presence. And to just update you, our next talk is scheduled on 16th July. And the talk will be delivered by Navratna University Professor Professor Yogesh Chaudhary, and the topic is transfer learning. And I would like to have a large number of presence in the same talk also. And with this, I once again thank Professor Jian Deng for giving a wonderful talk at this evening. And it is a great learning experience for all of us. And you enlighten us with the kind of work you are doing. And surely this particular topic, it is very hot topic in the area of mechanical engineering, and most of our students will like to associate with you on this particular topic and in future research. Thank you.
Thank you so much, sir, for your words. And thank you everyone for joining us today. We will connect in future too.
Pratik, can we take some photographs?
Yes, sir. Sure. Why not? Gabhav, sir?
You can take group photograph.
Thank you, Takamash. Thank you for your closing remarks. And thanks again, Ms. Kriti and Provost Neela. Thank you very much.
Thank you so much, Dr.
Thanks,
Deng.
Mike.
Thank you.
Thank you,
Gabhav,
Dr.
sir?
Deng. What
Have you
very,
taken the
very
group photograph?
fascinating work. Important work.
Thank you, Professor Michael. Thank you so much.
Thank you, Provost Neela. Always a pleasure. We'll continue to stay in touch and progress this collaboration. It's going well, and we'd love to see it continue.
So
Thank
next
you.
month, we are approaching towards our last talk in this series, and looking forward to have something new coming up.
Yes.
And that's right. We look forward to it as well. Have a good evening, everyone.
Thank you so much. Have a nice day.
Good one.
Bye, everyone.
Bye.